Hello, and welcome to Module 6. In the previous chapter, we classified a random variable as either discrete or continuous, where discrete assumes a countable number of discrete values. On the other hand, a continuous variable is uncountable. It is every value between an interval and can be very small decimal level value. Examples of a continuous random variable include the investment return on a mutual fund, the amount of time a patron may wait, or the amount of CO2 a company might emit. In this chapter, we'll focus on continuous variables, where in the previous chapter, we talked all about discrete. Most of this module is related to the normal distribution, which is the probability, the most fundamental continuous probability distribution. Other important continuous distributions we'll touch upon is the uniform, exponential, and the log-normal distribution. So let's dive in. Continuous probability distributions. Comparing to what we talked about last week, which was the discrete random variables, they had countable distinct values along their respective probabilities. This example on the left, where we can use a bar chart to represent the probability distribution of a discrete random variable. And remember, bar chart means we have these separate bins and we can calculate the frequency of a value that would occur within each bin. Compared to that to something like a histogram, which on the right is this continuous spectrum of values. And that's where we'll be talking about today for the normal variable. So a little bit of a refresh from last week too. When we were talking about discrete random variables, we can compute the probability of it assuming a specific value. Recall when we calculated the binomial random variable with a given probability of success or failure, we can calculate the probability of 2 successes in n trials. However, for a continuous random variable, we're unable to assign an exact probability to each of the uncountable values. This is because of the math or the integral of the cumulative distribution function, or that normal bell curve shape you see in this chart. And this is what makes the area under the curve equal to 1, is this cumulative distribution of probabilities, where we can't actually say for this specific bin what is that probability, but more approximate within an interval, what would that look like as far as the likelihood or probability. If we try to assign a non-zero probability to each of the uncountable values, there wouldn't really be any sense to that because it's this continuous spectrum. The area under the curve is proportional to the distribution of probabilities. Therefore, we use an interval to assign the probability. Similar, though, to the discrete random variables, we can use the cumulative distribution function to compute the probabilities along the interval spectrum. So we use this area under the curve to compute the probability. As we start to build more around this concept, let's begin with the uniform distribution, which is somewhat a little too, it kind of simplifies things in a way that is not super useful for a lot of cases, but we'll talk about why it works and what it does as a good building block for us to get into something like the normal distribution, which has more applications in real life. But for now, let's start with the uniform distribution as a somewhat overly simplistic way to measure this type of probability. And the reason I say it's simple is because this distribution occurs when the underlying random variable has an equally likely chance of assuming a value within a specified range. That's what gives the name uniform. It's not more likely given different values. It's all uniform likelihood across the range. Some examples of this is the approximate delivery time of a shipment, the scheduled time of a flight, or the waiting time for a train. So for example, suppose you're waiting for a shipment to arrive between 2 o'clock and 3 p.m. That's the window interval they give you. We can think about the probability that the shipment will arrive as a random variable x. We have a total of 60 minutes of our range from 2 to 3 p.m. And this shipment could arrive at any minute throughout that entire hour interval. But we can break this down a little bit and infer that the probability of delivery between 2 and 2:30, which would be halfway between 2 and 3, would roughly be equivalent to half of the probability of receiving your shipment for the entire hour. Similarly, we can slice up the probability on the other side and say it's half as likely to arrive between 2:30 to 3. We can also slice and dice this in other ways by using 15-minute intervals and think about there's a 25% chance the shipment will arrive between 2 to 2:15, 2:15 to 2:30, and so on and so forth. So the concept of this is we can break out the time intervals and think about the probability within each interval. But again, because this is uniform, the likelihood can be broken out into these nice equal slices. On the left, we see a depiction of the probability density function for a continuous uniform random variable. We use the values of A and B to represent the upper and lower bounds, such as 2 o'clock to 3 p.m. in that shipment example, because this is the probability that we want to think about across this interval. The entire distribution is also symmetric around the mean. We don't have these tailedness, there's no skewness, again, because it's uniform. So because of this, it looks like a rectangle, and therefore we can apply geometry to calculate the probability of receiving the shipment at a time interval. Because we can use this area of the length times width. And because we know this area under the curve is the cumulative probability, and thinking again of that hour broken down into each 15-minute interval, when we add all those 15-minute intervals together, we'll get to 1, or 100% of the probability that your shipment will arrive within this interval. So it's important to emphasize that the height of the probability density function does not directly represent a probability, but rather this distribution between intervals. And this will have a little bit more of other examples to drive that point home of like how we actually use this probability density function to inform the likelihood of something happening. For other summary statistics to calculate, so similar in the homework, you'll be needing to calculate the mean and standard deviation of a uniform distribution. These are the formulas you would use, where you have A plus B over 2 for that mean. And again, that's kind of like finding the middle ground between the two intervals to say that's the average. Similarly, with the standard deviation, you would have B minus A squared divided by 12, and you take the square root of that. And those formulas can be pretty much plug and play to be able to calculate these different summary statistics. So let's talk about calculating this a little bit. For the mean of our example, we would take that middle value of 230 to be the mean, because we take the lower bound, higher bound, and divide that by 2. So we can say, on average, you should maybe expect to get your package by 2:30. But again, that probability can split up depending on the interval that you're looking at. But for the average, it's a kind of a simple way to say when you might expect to see your package. But let's extend this to the normal distribution. And throughout this chapter, throughout this class, we've touched upon the normal distribution before as we talked about variance and probability. And it's that familiar bell-shaped distribution, also referred to as the Gaussian distribution. And this is used extensively throughout statistics. And the reason for this is because of how many things in life the normal distribution can be applied to resemble this probability distribution. One example, recently I went out for dim sum with some friends and noticed that the bill actually had a relatively normal distribution where you had the price of the different entrees we ordered, and most of our entrees were in this middle round region, and we had a few that were more pricey and a few that were less pricey. And I just found it interesting. Hey, it looks normally distributed. So I would encourage you to think on any walk you take, thinking about how these types of approximations of likelihood and probabilities can be applied to other things you might come across. But other examples of random variables that closely follow a normal distribution could be salaries for employees, the rate of return on an investment, average R&D expenditures, and so on and so forth. There's really a lot of different things that can be thought about in the probability of happening that are normally distributed when they follow this type of pattern of being symmetric around the mean, where we have the majority of those food prices that we ordered were around the middle, and then we had those tailoredness to know what the likelihood of having a meal that was above or below the general mean might look like. So it's important to analyze the underlying data in order to determine if the normal distribution is appropriate in the scenario. And towards the end of this class, we'll actually talk about how we can measure if a distribution is actually normal. But for the majority of the homeworks, we will just assume that the data is normally distributed. So what all that is saying is just assume it's normal, but sometimes it might not really be. But at the end of this class, we'll have the tools to really be able to measure if it is normal or not. So in previous chapters, we explored some of these methods when we looked at a histogram and box plots for the symmetric distribution. In most instances, again, we'll assume normalcy. And then the test that we'll use in the end of the chapter is called the chi-square test for normality. And we'll use that to make sure our assumptions are valid. But for now, we'll normally just say, assume the distribution is normal. So this visual just shows the weight in pounds of newborn weights. And you can see on average, the weight is about 7.5 pounds. And this is symmetric because the left and the right side of this distribution relatively mirror each other. And you have this nice smooth curve where we can start to see this distribution around the mean. And that's what gives that bell-shaped name of the bell curve. And it's also, I want to talk about it being asymptotic, which we also talked a little bit about last time, which means the tails approach the horizontal or x-axis on both sides, but never fully reach it. So again, we talked about how the area under the curve is considered to be 1, but really it's 0.9999999 because it never actually touches it, but because it approaches infinity. You know, for newborn weights, there could be something that is totally outside of this spectrum that we didn't see, but we don't necessarily calculate that. We just assume this infinite distribution. But let's start to go through an example of how we would actually start to calculate the mean and use this distribution to inform our understanding about how the data would look like for any type of case study. So suppose you're looking to market a new product and you want to know different social media platforms that might be a good fit given your product. And you know that different platforms tend to have a different audience base that use the platform. So I just took a couple of examples like Twitter, TikTok, and Facebook. Those are the 3 options we're going to consider for marketing your new product, and you want to know which is the best fit, given that your product fits a specific type of demographic of age that you're looking to market for. So we can now start to use these different metrics of the mean and the standard deviation to know which platform is likely to have the clientele that you'd be looking to market to. So, and again, we're assuming that these are normally distributed. We don't have any types of skewedness. We have this nice normal curve where the majority of users on Twitter, for example, are 25, and the standard deviation is 8 years above and below this. For TikTok, the average age is 18, but maybe this varies by 10 years above or below. And for something like Facebook, the average is 40 and the standard deviation is 25. And these are numbers that are generally based off of a quick Google search I did, but they're actually somewhat similar to what the statistics showed of some survey that they did. So I think it's just kind of interesting to see the differences. But again, thinking about how this chart takes these summary statistics it's kind of difficult to really interpret the overlap and difference between the demographics, particularly if you're interested in targeting content to reach this specific age group. You want to see, can I go on all three? Should I only look at one? What's the overlap between these? How much of the variance exists between the social media platforms? So let's graph it and see what this might look like. So we'll hop to our demo, where I'll be hopping back and forth between the demo and the slide, similar to the last class, as we talk about the different distributions. So, oops, I think I skipped the uniform distribution here. But this would be, before we go into this case study with the social media, let me just talk through the code for the uniform distribution. Because the homework will look very similar to this, where you'll have some type of question about sales or some type of distribution, and say that it follows a normal, a uniform distribution, and you have that lower limit and upper limit. We have here for how we can calculate the mean and standard deviation. So we can define our intervals where we would have A is equal to 2,500 and B is equal to 5,000 for this sales question. And we want to know the mean and standard deviation. And I just want to talk about this real quick. It shouldn't take too much time, mostly because the formulas were relatively straightforward, and I just built a function that will take that formula for the mean and for the standard deviation, and you plug in these lower and upper value bounds, and we can start to see what that output would look like if we were to plug it in. So we can say the mean is about 3,700. And again, that's just taking the middle between those two values, and the standard deviation is about $7,000. And this starts to visualize what that would look like. And because we're going to be taking a random sample from a uniform distribution, we need to set our seed to ensure that our results can be reproduced if someone else were to take our code and try to run this again. So that's why we set the seed, to make sure that if we were to instantiate this distribution again, that we would see that same output. So this line of code takes from the NumPy package a random sample from the uniform distribution. And we say, starting from our lower bound to our upper bound, take 100 samples. And this is what that might look like. And because this is almost a simulation, we can start to calculate the mean from this, because we're simulating a uniform distribution throughout these intervals, where if the sales team might make a little bit above and below this upper limit value, we could see what those values would be. And we can just use the mean to calculate what that would look like based off this simulation. So let's see how that compares of 3,600 compared to the mean, which is just below using that formula would output, which is, again, we're using formulas to generalize the pattern that we might expect to see, compared to using a simulation, which you could actually output some likely values and calculate the mean for something like that. So I always find it interesting when formulas do a good job of actually approximating what you would expect to see when you run a simulation. So let's start to plot what that would look like. And again, this is from that uniform distribution, where we start to see the values from our different range intervals, and we have this relatively uniform distribution for the different bins and what the probability is for what we'll see. And compare this. This is discrete, where each value, and it doesn't really look very pretty. That's why I didn't add too many like axis labels or interpretation. It's really just to show you how this uniform distribution would look as discrete values compared to a continuous spectrum, which has this now area under the curve, which now we kind of start to see some subtle nuances from that sample. If we wanted to solve for the probability that sales exceeded over a certain value, we would calculate the height and then take that difference between the value and the upper bound area. And we would start to see that now, because we're looking for above 40,000, that we would subtract that from the upper bound and get that probability of that area under the curve because we're multiplying it by the height. So we can say the probability that sales are between these values is 0.4. Now, if we wanted to talk about probability that sales are between a specific interval, we would slice the area in a similar way. In this case, we only want the area between the interval. So rather than subtract it from that upper interval, we'll take that interval between those two values of 3,200 and 3,800. So we would define those values, and then we would take that area between. Again, as we're thinking of like how we slice the minutes of 15 intervals, we can think of this probability as being uniform. So we can take this interval between, and now we can multiply that width by that height to get the probability. And to say the likelihood or probability of seeing sales between 3,200 and 3,800 is 0.24. So judging from this, it's more likely that you'll see sales between 40 to 50 compared to 32 and 38. And really, this isn't because of anything other than the interval being wider. Like there's more chances from 40 to 50 because that interval is wider compared to 32 to 38, which is looking at 6,000 difference compared to 10,000. And that's again because that uniform distribution. Apologies for skipping around a little bit. I should have done that demo before diving into this about our little case study, but now we've reached the case study point. So just to refresh from that little tangent, we're talking about the different values of social media user age and how we can start to use this mean and standard deviation to approximate the likelihood of seeing a user on this platform that might fit your target market demographic. And here I just define the mean and standard deviation based off of that table that we had in the presentation slide, where we have the different means and the standard deviation for each platform, where Twitter and TT stands for TikTok, FB, or maybe Meta would be more fitting, but we'll just keep it Facebook for now. And I just want to emphasize this little bit of code case study is not needed for the homework. It is just for demonstration purposes for us to look at how we can visualize these numbers and see what that distribution would look like, because we'll start to use that area under the curve. And I will continuously say, when in doubt, draw a picture and use paper and look at how the distribution might visually compare before you start to calculate anything. So that's why I wanted to show this code. So if you wanted to visualize what that distribution would look like, you would have those tools in your pocket. So this function that I built, and when I use function, think of it as a little tool that you can then use and plug in new numbers and have that output. So kind of think of it as like a Lego block, where now you can use this block for new things and it'll output what you're looking for. So if you wanted to take this, you don't need to redefine the different formulas. You would just use this building block to input your new values again. So I'm enjoying seeing on homeworks people using functions, but you don't need to redefine it once you use it once. Think of it again as like you have this building block, you can now use it on new things. You don't need to redefine that building block. So what this function specifically does is that it creates different X observations along the horizontal axis, given the distribution of a normal curve. So it takes just the different values along the x-axis. It'll take 100 of them, where you have the difference from the mean minus 3 standard deviations to the left to 3 standard deviations above the right. So this is just defining our horizontal axis and saying from the mean, start 3 standard deviations to the left and 3 standard deviations to the right, because that's what we'll want to start to plot that normal distribution off of. And throughout this chapter, we'll start to see this function more, where we're using the stats package and taking the different probability density functions to output what a value might look like. So there's a lot of different resources in these stats packages, and we'll start to explore what those different tools can be used for. But for this distribution, it will just create a density function, which is what will show that curve for every value of our x-axis given our mean and standard deviation. So we're using this function now for each of our social media platforms. We'll say we're going to plot these, but for now, we just want to get the points for each of these. So for Twitter, TikTok, Facebook, we use that little building block of this function of norm distribution coordinates, and we input the mean and standard deviation for each. So let's just peek under the hood what that might look like for Twitter X. And again, if you're ever curious about what's going on inside of a function, I always encourage you to take it apart and explore each little piece before you put it back together. So something like this, for Twitter, we see the values of X are somewhere between 1 and 3, and the values for Y, which those are each value along the x-axis, where Y, we start to see these very small probabilities, which will be that area under the curve. And now we can just plot what those would look like together. And this is kind of that aha moment that we now can see. Before I talk about that, let's just say what this code is doing. Remember, this defines our canvas size. And now for each distribution, we can just plot each one on the same curve. So we plot Twitter. Each time I call that plot, it's plotting the different distributions we just created. Plot Facebook. And then this just adds labels. Okay. But now, because we have those different mean and standard deviations, and we took that probability function throughout the intervals for this different social media platform, we can now really start to see the differences and similarities between the different platforms. So let's first talk perhaps Facebook, where we see 40 is the average age, but because there is that high standard deviation and variance, that the range can go anywhere. And again, this doesn't really make any intuitive sense. No one can be a negative age. And I do question how many people who are 100 are scrolling on Facebook every day. Whereas sometimes these tails don't necessarily make sense. So in real life, these would likely be capped. But again, for just demonstration purposes, we assume normal, which is like this perfect bell-shaped curve. But we can start to see that that variance is wider because the standard deviation was higher, where let's just hop back to that table where the standard deviation was 25 years compared to TikTok and Twitter, which have this kind of narrower, tighter distribution. And it's very visible to see where TikTok has a little bit of a younger demographic as the peak of just below 20 years old, where Twitter has this distribution between a little bit above the age of 20. But there is a lot of overlap between users who might use Twitter compared to TikTok. But you start to see there is a gap between that, where there's a younger age that uses TikTok that might not actually use Twitter. So again, we can use these types of distributions to start to get a general understanding of the likely value, or like the random variable of age you would expect to see on this type of continuous spectrum. So in short, you might be more likely to see someone who's 60 using Facebook compared to someone 60 using TikTok based on this distribution. That's pretty intuitive to see compared to something like 20. They might be using all three platforms. All right, back to the slides. We use these different parameters to start to be able to understand these patterns. So this is what that graph looks like that we just walked through. And we use this distribution function to now compute the probability for a variable under this curve. So as I talked about the probability of being 60, we can now start to use those values as a way to infer probabilities. Next, we'll discuss how we can calculate the exact probabilities of certain values. So we first look at something called the standard normal distribution, which, as we're looking here where this goes to negative ages, that's just because we're taking this standard normal distribution type of representation. So this will be the bulk of where the homework assignments will stem from, this standard normal distribution, which is a special case of the normal distribution, where it just takes this like perfect equal 0.5 probability on either side. And think of this standard normal distribution similar to the unit circle from math class, from any different aspects of when you're starting to measure the different radians and sine curve. You use that unit circle. This is kind of the same thing where we have these calculated values for specific inputs. So this instance, the mean is equal to 0 always, and the standard deviation is equal to 1. We use the letter z to denote the value that the random variable may assume. And this is the same z-score value we discussed previously. And this z-score measures the number of standard deviations a given value is away from the mean. For example, a z-score of 2 implies that the given value is 2 standard deviations above the mean. But again, what's handy about this z-score is that it doesn't take that unit into comparison. So we can now convert the z-score into other things because we're standardizing the data. And now we can use that to compare distributions between different scales. So thinking back to our prior example of ages between different distributions, using something like the z-score to compare an age provides us with a standard value independent of any scaled differences, because we're taking that value, comparing it against the overall distribution rather than any specific scale in that distribution. And there's different ways we can calculate these probabilities. First, I'll use the textbook scenario where we have this table of pre-calculated probabilities. Because we have this standard normal distribution, we can already calculate all the different ways you can slice and dice this. And that's really what is in this table that you find in the back of most statistics textbooks. So we'll go through how we can use this table to calculate the probability of seeing a value above or below, or even a specific value. But then we'll also use different probability distributions to approximate this as well. So when these calculations of probability first started, they were recorded in a table and used as reference called the z-table, because we didn't all have Python to be able to calculate these things. You were able to use a table to simplify it and to create your calculations based off of. And this z-table provides the areas or probabilities under the z-curve. And you might see different versions of how it looks like, but because sometimes they'll take the value above, sometimes below. So there might be subtle nuances between the different z-curve and z-table charts. But once we learn how they're used, you can then have that understanding to know how they might compare between different textbooks. But in ours, this is a screenshot of what it looks like. And they have 2 tables, which is kind of handy, as long as that's why it's very important to know how they're different and how you can interpret them, because these 2 different tables, one is used when the z value is less than or equal to 0. The other is for when the z value is positive or greater than 0. I'll continue to say, when in doubt, let's start by drawing the curve and looking at the symmetry to get familiar with where we should be even looking to compute the area under the curve. And that will help us determine which table to use. So just again, we're starting just by using this table, and later I'll use Python to calculate the same values. But I think it's always good to know how we can use these tools in different ways, but they calculate the same thing. So let's look at this distribution on the left. It represents the standard normal probability density function because the random variable z, uppercase, is symmetric around the mean of 0. Therefore, we can say the probability on either side of this middle is 0.5, since the area under the curve equals 1, and because it's perfectly symmetric. We can use our z-table to calculate the z-score for this probability distribution. Let's consider a value that is 1.52 standard deviations above the mean. The z-score is 1.52. That's really what z-score is saying. How many standard deviations above or below the mean is it? And because it's positive, we know it's above the mean. If we drew this on a normal distribution curve, it would be on the positive side and look something like this. Now, because we know which table to use, we're using the positive one rather than the negative one. We would use this table. I just took a screenshot from the appendix and follow the table that provides the cumulative probabilities that are under the curve to the left of z, because we're looking for anything that is below this z-score. So using this table, we would then skim down to the column of the z column until we find a value that closely matches the z-score we are looking for. We then look across the rows to find the exact decimal place of the z-score. Think of it as you're using the 10th place in that first column, and then you move to the right to find the right 100th place to look up in the table. So since this is 1.52, we find the 1.5 in the first column and then shift to the right until we are in the right 100th column to 0.02. And this is where we now converted that z-score of 1.52, and we're trying to calculate the probability of anything below this value. So what would you expect to see of any z value, like a random value of z under this z-score of 1.52, which is 1.52 standard deviations above the mean. And now we use this z-score table to calculate the probability, and you get a value of 0.9357. But what does this actually mean? And that's why I think having the curve drawn out is really important, to make sure that these numbers intuitively make sense to you, because that 0.9357 is that area under the curve to the left of that value, where if we look at this table, we see that 0.9357 is almost just about 1, which would be that total area under the curve, which means that it's very likely that you would see a value within this range, because it's almost 93% probability that a value would fall anywhere below this threshold. So any value in the green side of the probability distribution is considered to be probable. The area on the right, or the yellow side of the curve, is the other part of the probability. So if we were to subtract 0.9357 from 1, we will see that the probability of a value above this threshold, if we were to get something above 1.5 standard deviations above the mean, would be 0.0643. And again, that was just by taking, like, we can really play around by slicing and dicing this to say anything above this threshold by simply just subtracting anything below the threshold by 1. So by subtracting 0.9357 from 1, we have the area on the other side of the curve, which would be 0.0643, or about 6 6% probability, which is not out of the question, but it's a lot less likely than 93% of the values, which will be below the curve. And bringing this back to that age distribution, what would be the probability of seeing someone on Facebook that's 1.52 standard deviations above the mean? We can now start to say the probability of seeing someone in this age demographic is a lot higher compared to seeing someone who's way far away from that mean. You know, say someone who's 100 years old, the probability of seeing that is a lot lower than seeing somebody who's 40 years old. But we're going to go through a bunch of examples until this really drives home, because I think it could get confusing when it comes to which chart to use and how we actually slice and dice it to know, should we be using positive or negative? But really, once the concepts make more sense, using that picture and thinking it through, you can really use the tables in lots of different ways. But we'll start to just go through the different patterns of what you should do, kind of like these sequential steps to get you the right answer. So in that last example, we talked about the values below this number, and we're going to talk about the same thing, but now a value that is below the mean. So again, if you were to calculate this from scratch and you have a z-score of 1.52, I would want you to create that normal distribution, draw a line of where you think that z-score is, and then we're thinking anything below this value. So we can then just color in everything below that. So let's start from scratch here. If we were considering the probability of a value of z that's less than negative 1.96, again, let's consider drawing this curve. We create a line at negative 1.96, which would be 1.96 standard deviations below the mean. And we're looking to calculate anything less or equal to this value. And this would equate to that little area of anything in green on the left. And the rest is yellow. So using the appendix, and they have nice little pictures, so now you can compare what it is that you're doing is the appropriate table to use, which they look very similar. We're calculating now just that little tail to the left side. And we use the same exact approach of using that z column to find the tenths place for a value that's similar to this. So in this case, we would go all the way down to negative 1.9 and then shift all the way to the right to negative 1.9.025, which, or 0.06, my apologies, which would output 0.025. Which, when we think about this now on that table, the probability of seeing a value below this threshold is about 2%, which, going back to a couple chapters when we talked about Chebyshev's theorem and how you can think about these different variants and the probability of seeing a value below this, it's that same distribution of values where we now have in the tails that a smaller portion of those values will reach those tails. So everything should really start to be building off of each module at this point. So similar to our last example, to calculate the area on the right side of this, if we wanted to take that other side of the pie, we could just subtract this probability of 0.0250 from 1 to know what's the probability of seeing anything that's greater than this negative 1.96. And not to complicate things too much, but that's why I say you can use these tables in lots of different ways, because you can actually take this same value and use the other table and subtract it from 1. So once you really get kind of more confidence in using these different tables, you can use them depending on which approach you find most comfortable to you, because they're really looking at different things of the same coin. But let's go through a few more examples where we calculate the probability given two values, since most of the time this will be the most common use of the probability distribution and similar to what the homeworks will look like. And rather than think about all the values that can occur below a threshold, we want to know the likelihood of seeing a value between two intervals, which kind of gets things a little bit more interesting. So let's start with calculating the probability of seeing a value that falls between 0 and 1.96 standard deviations above the mean. And this will be very similar to what your homework question would look like. So what do? We draw it. I just drew some stuff using slides, but again, I would recommend having a piece of scrap paper near you and start to just draw what this might look like. So you can think about how are we slicing this probability distribution. So I drew what 1.96 above the mean would look like. And then the mean 0 is the mean. It's not anything above or below. So we know right in the middle that we would be taking this type of interval. So, and I just shaded in what is it that we're trying to calculate for, which is that Z in the middle. So now that we have our picture, we now know which table in the appendix we can use because we're using anything above the mean on the positive side. So this would be similar to that first example we just walked through. But now because we're not using anything above this, we're using this just interval, we need to remove that little portion that's above that 1.96 value. And the way we do this is by subtracting that, what we just calculated in the last one, from the whole area that would be in that side. So using the table that has the probabilities to the right of the mean, we see that the probability of 1.96 standard deviations above the mean is 0.9750. And the way you would get that value is exactly what we just went through in those last two examples, where you would go down the tenths and go to the right to find the right hundredths. And you would get that probability. So the probability of 0 standard deviations above the mean is 0.5. And now we subtract those areas from each other to leave ourselves with just the part in the middle. So since the table finds the probability of everything below the value, the overlap between these two probabilities is exactly the value we're looking for. So again, just think about this area under the curve. Everything needs to equal 1 if we were to add everything together. Again, I'm just talking through these points multiple times to drive the theory home of how we use these cumulative distributions to understand probability, where even in this example, everything to the left of that curve would be 0.5, everything to the right would be 0.5. And now we're starting to split that to be just this interval we're looking for. And because we now have these probabilities converted from the z-score, we can get exactly the value we're looking for. And so now we can say the probability of seeing a value anywhere between the mean and 1.96 standard deviations above the mean is about 47%, which, going back to our understanding of the normal distribution, this should make intuitive sense that it's pretty likely that you'll see a value in this range. So that's a good way just to check yourself against the picture you drew, because this area is so high and it's really right in that middle where the majority of our values would be. About a 50% chance that a value would be here makes intuitive sense compared to something all the way in the tail where it'd be very unlikely to perhaps see that value. All right, now let's go the opposite way, where we start with the probability and we convert that to the z-score, because these are, again, it's a very helpful tool to be able to convert between z-score back to probability and vice versa. And because the z-score is like scale independent, it's we can do these things and now start to compare between different distributions. Okay, so what would we need to do to be able to convert this z-score? We would start to think about the probability that the z value is less than or equal to 0.6808, for example. So first, let's think about what this might look like. We know that since the z-score is greater than 0.5, that it must be on the right side of the curve. So we don't necessarily need to know how far up the curve until we have the number of standard deviations. But since we're looking for a value that is 0.6808, we can think that it's slightly above the middle of 0.5. So again, I'm just going back a couple when we're talking about this 0.5 of this. So we know that a z right in the middle is 0.5. So now a z that's slightly above that, we know that it's slightly positive, but probably around this middle ground level. So back to our example where we're looking for a z-score of 0.68. And now we want to convert this to the z-score because this is the probability and we want to convert that to the z-score. So we can assume that it would look something like this, where it's not right in the middle, but it's just a little bit to the right, where we know it's not 0.5 under the curve, but it's just 0.68. So it's a little bit more than that. But this is just needed so that we know which table to use. So you don't have to worry about getting it exactly in a place where you might expect. And this time we work backwards using the table. And we know that would probably be close to that 0.0 since it's right near the mean, which would be the z-score of 0. But we'll just need to skim until we find our exact cumulative probability value, which is 0.6808. And we see that it's in the 0.47 standard deviations above the mean. And think back to the area we have shaded under the curve. About 68% of the area is filled, and we can think that there is a 68% chance that we would see a value that would be at least 0.47 standard deviations above the mean or anything below this. Next, we'll go through an example where the probability is less than 0.5. So this one, the probability was just above 0.5, and now we know what that z-score would be given this probability. Okay, so in this case, we're calculating anything. What's the z-score for the probability of 0.0643? And because this is less than 0.5, we can start thinking about how this might look as a curve, and it would be to the left of the mean. And since this is much smaller than 0.5, we know that it might be closer to the tail on the left-hand side, since it will only be taking up a small portion of the entire area under the curve. So let's draw this out. And we can assume it to look something like this, with just the left-hand side tail filled in to about 0.0643 of the entire area under the curve. Now we can use the table that is on the negative side in the appendix and find the corresponding probability. And actually 0.0643 is the area under the curve that is given at the top of the table example, which just worked out in this case. So the z-score is negative 1.52. And if we didn't happen to see that example using the table, we would use that same approach of scoping out the approximate digit we are looking to see, where we would expect to start with 0.06 and work our way across the z-table to the exact value of 0.0643. And we would know that the z-score is negative 1.52. So now we can translate this back to our mean, and this would be negative 1.52 standard deviations below the mean. and seeing a probability of a value below this in this tail is pretty unlikely at about a 6% chance. Let's go through one more example that has an interval now between the two values under the area of the curve where we need to find the z-score. So these start to get a little bit more tricky, but as we hammer this idea home, we can get exactly what we're looking for. So in this case, we're looking for the z-score that has a probability below and above these different z-scores that will result in 95% of the area under the curve, or 0.95 of probability. And now at this point, we should know 95% of the area would pretty much be the majority of the distribution. And because it's symmetrical, we would think about this on both sides of the mean. And I want, before you move forward, draw it out and see what you think it would look like. Like hit pause and draw it out. And then I'll show you what it would look like. Since the curve is symmetric, we know that the majority of the area will be in the middle. But how do we calculate the z-scores? And this is what the picture would look like, because we have this bulk of the majority above and below the mean, and it's 95%. So we're thinking of everything except for those two little tails on both sides. And one way we can do this is to just subtract out those tails to know what this majority would be in the middle. So the way we do that is to subtract that 0.95 from 1 to get that area outside of this interval, which would be 0.05. But we want to split that between the two tails on both sides of that curve. So we would just simply divide that in half. So in each tail, negative and positive side, it would be 0.025 on both sides. So we use those because we need to now look at that z-score table to know where the value would look like, and then we would just add those between the two intervals. So there are two different ways we can calculate this. The one that makes most sense to me would be to use the negative side of the area of 0.025 and find the z-score of negative 1.96. And knowing that this would be symmetrical on both sides, we can declare the interval being from negative 1.96 to positive 1.96. The other approach would be to add 0.95 to the positive tail of 0.025 and find the z-score for 0.975, which is positive 1.96. So please feel free to follow up with any questions in our Slack channel if more examples would be helpful. A lot of these were just derived from the textbook, and I just talked them out a little bit further. So there are a lot of examples that go beyond what this scope was in the presentation in the textbook as well. And next, we will discuss how we can apply this to normal random variables, where it's not exactly 0 as the mean and 1 as the standard deviation, but we use this same approach of knowing the area under the curve to calculate the probabilities, convert that back to a z-score to know how this might compare to the mean having the standard deviations above or below. So you'll start to see this same approach can be used to derive the relevant probabilities that we're after. I want to take a step back and first talk, why do we even use any of this? Why are distributions used? Why do we care about the area under the curve? And the answer is because it helps us represent the patterns that arise when something is normally distributed, which is a lot of random things in life. Talking back to that first slide where I showed you the dim sum bill, I'd want to encourage you to take a walk outside and start to think about a lot of the different things that could be represented by normal distributions. Think about the diameter of nearby trees, for example, the number of bikes locked to a bike rack throughout the day, or how many times the word "the" appears in a magazine. Once we have this type of framework of counting these occurrences and starting to see how often a value would appear, we can start to identify the mean and standard deviation of the data, which could then be used to inform our expectations of what future data points might look like. So for example, if you took the diameter of nearby trees, you can start to know how it might compare to each other. And so you could say the average tree diameter is, 26 centimeters in your area, and thinking about how something might compare above or below this. But perhaps the bike example could be a more interesting one if you're trying to think the probability of you getting a bike parking spot throughout the day. You can start to measure how many bikes you see and get that average. And now you can know probability of you getting a bike spot is pretty high at this time of the day. But I just want to draw these kind of abstract statistics back to the real world and why we might want to care about this. One other just kind of interesting concept that I want to discuss for why this might be interesting is about the Pareto principle, which is also known as the 80-20 rule. And again, this is a bit of a tangent, just want to talk about it because it's interesting, where this rule suggests that 20% of your activities will account for 80% of your results. This finding represents large characteristic variations in our society and nature. Pareto's observation was in connection with population and wealth, where he noticed that approximately 80% of Italy's land was owned by 20% of the population. It's also an adage of business management that 80% of sales come from 20% of clients. So I bring this up to talk about how we can think about the area under the curve, where we consider the distribution of a variable and how we can use it to better model patterns in the world. So back to thinking, if you're thinking about how 80% of your sales come from 20% of clients, how does that distribution play out? And maybe where should you be focusing on that business development? So just thinking about your life and how perhaps, you wear 80% of the same things in your closet. You wear 20% of the same things in your closet 80% of the time. You kind of start to drive on just 20% of the same roads that exist in your neighborhood 80% of the time. So kind of just thinking about how things play out and thinking about this normal distribution in real life. Okay, back to how we can use these normal random variables to transform the probability of seeing a specific value. Any of these normally distributed random variables, again, anytime you hear assume this distribution is normal, we can standardize it into the format we just reviewed, where the mean of 0 and the standard deviation of 1, which will allow us to then use the z-table for just about everything. And the way we do this is to transform x into z by subtracting from x the mean and dividing by the standard deviation. And this is called a standard transformation and helps us compare between different variables and scales. In data science, we often need to standardize or normalize our data so we can compare different scales of data, such as comparing the population density to the number of schools in an area to predict the needs of the area. So once we use these scale independent transformations, where we're essentially taking the relative distribution, we can now start to compare different apples to apples in a way that is comparable. So let's go through an example using the table, and we'll then use Python to calculate the exact probabilities without using the table. So some of these formulas we're talking about should be familiar, like that z-score formula here, where you take x and subtract from the mean and divide by the standard deviation to know where this value would lie. let's go through an example, and this will be similar to what your homework will look like. And I just applied it to the ESG world because in my previous company, we developed different ESG scores, and you might start to see scores for lots of different things, which I won't get into kind of the different implications a score might have. But if you were to have this type of metric of ESG score, which should essentially approximate a company's long-term sustainability metrics, and we have a bunch of scores for different companies, and the mean is a score of 72 and standard deviation of 8. So first, let's use this distribution of company ESG scores to start to understand how probability would play out. So what is the probability that a randomly selected company will score above 60? And what is the probability that a selected company will score between an interval? So we're taking those same concepts we just walked through, applying it to a more real world example. And now we can start to understand the probability of what we would expect to see. So before we go through, what are we going to do? We're going to draw it. We're going to draw what this distribution might look like. Okay. So what I would do once you have these specific inputs, we know it's normally distributed. Again, just assume normal distributed when we're talking about anything in the normal distribution chapter. And we have this average of 72. We can mark that right in the middle of what the mean. And then I just added a standard deviation above and below just by taking that 8 and adding it to 72 and subtracting it. Just this gives me a good understanding of what I would expect to see one standard deviation above and below, because now we can bring that back to the questions of the values we're looking to approximate. And we will draw our example problems. So what is the probability that a randomly selected company will score above 60 on this ESG performance scale? We would fill in the area to the right of the curve, and we can use our new formula to calculate the z-score and use our table to find the associated probability. Since our value of x is 60, we plug this right into our formula and subtract the mean and divide by the standard deviation. So 60, the value we're looking for, subtract from the mean, divide by the standard deviation. And this equates to negative 1.5. But since we're using the area above this value, we can still use the positive table, and we'll find the area under the curve to be 0.9332, or the probability that a randomly selected company will score above 60 on their ESG score. And let's move into Python to calculate the z-score of that other example as well. Okay, so how we would walk through this, where I usually like to define just our variables of what is it that we're using. Because now we have it defined, now we can call these variables and use it in our varying different functions that we've developed. So from just the input of knowing normal distribution, mean of 72, standard deviation of 8, I just define it using a label that makes sense to me of mu and STD for standard deviation. So first, we can use that function I walked through before when we were looking at the age, just to get a good sense of what this might look like, where similar to that graph I drew out by hand, we see the average right in the middle of 72, and we can start to see these tails of where a company might perform. And we see, because of that standard deviation being 8, it's somewhat of a relatively steep middle, where most of the companies would probably fall between these parameters. So rather than using the table and using that z-score conversion that we walked through in the slides, we will use this stats package from the normal distribution and calculate the cumulative density function for this value. So the value we're looking to calculate for x is 60. So we define that, and we're looking for anything above 60. So this output will give us the cumulative distribution, and we want to subtract that from that. So that pretty much means the cumulative distribution below that 60. And because we want everything above that, we subtract it from 1. So that's why it's really important. Just take a step back, think about what is it that this table or that this function would output, where this function, this cumulative density function, gives you everything up into the point. And since we want to know everything above 60, we would have to subtract that cumulative distribution function from 1 because we're looking for that other side of the coin. So similar to when we had that 95 distribution, we could just subtract the tails from the middle. This is all, again, just similar steps of patterns of take the value, draw it out, see what you're calculating for. Is it above or below? And using either the table or you can use Python to calculate these different probabilities. So I subtract from that, and we have, now you don't even need to use the table. We have the exact probability of seeing a value above 60 is 93%, which again, now thinking if you were to draw that in, you would expect to have the area under the curve all shaded in above that value. And yeah, that makes sense that 93% of all companies that are scored would expect to be above this value. And now, since we have this little function, we can start to use it to calculate the probability between two different values. And again, this is just different ways to solve the same thing compared to using the table where you would calculate the probability for each interval and then subtract from each other. We would now use this stats norm cumulative density function and just subtract those probabilities from each other if we're looking to get an interval between 68 and 84, for example. So I will just redefine x instead of just calculating for one. We're calculating for both 68 and 84. And now we would subtract those from each other and start to see that the probability of getting a value between 68 to 84 is about 62% of probability. So it's pretty likely that a company, it's even, so it's, you could say with higher confidence that a company would score above a 60 because 93% of companies do. And if you wanted to get a little bit more granular to say probability a company will score between 68 and 84, we can say that the probability is about a 62% chance. And that should explore the reasons for why we use this normal distribution to kind of generalize what we'd expect to see. And we can start to now use that to inform probability of the expected outcome. Next, we'll be talking about the exponential distribution. So up until this point, we've talked about the uniform, which I really just wanted to talk about mostly to start to dip our toe in the water about this area under the curve. But this normal distribution is definitely the crux of statistics in kind of the fundamental sense. And the normal distribution is used for a lot of different things because of its applicability to a lot of things. But now I'll talk about a couple of other continuous distributions, mostly to explore other patterns that aren't normal, and also just to challenge ourselves beyond this just normal distribution and understand more continuous distributions. So actually similar to what we talked about in the last class, when we had that discrete distribution of the Poisson, we can compare that to an analogous one that's continuous, which is the exponential. So we'll talk about this exponential distribution, which is closely related to the Poisson. So this will be a nice review from the last chapter, but building on a little bit, where recall previously we talked about this Poisson distribution and how it's used to calculate the probability that an event will happen within a time interval, such as how many customers will buy coffee from the Starbucks that you're a manager of over a particular time period. The exponential distribution looks at this similar type of rate, but rather than the number of occurrences that happen, it looks at the time between the events, such as how much time occurs between something like replacing a component in a factory and when it degrades and must be replaced. And that's actually, that's a really valuable thing to know for any type of preventative maintenance. If you're in a factory, you want to know, how do you optimize the cost that it would take to replace something based on how long it can be used to still have its structural integrity, for example. So we can use something like the exponential distribution to start to measure the likely amount of time it would take to elapse before needing to replace something, which would be really very costly if it were to fail. So how do you use these types of probabilities to inform that decision? We would use this exponential distribution in this case. So on the right, this is what the exponential distribution looks like. It is non-negative and approaches the x-axis in a similar asymptotic way as the normal distribution. So you can kind of think of this is like the tail of a normal distribution, in the same sense that it never actually reaches 0 on the x-axis, as it's asymptotically approaching it. And we have this lambda rate, which is similar to the Poisson, and we'll talk a little bit more about how this is used. But in this case, think about this lambda rate being the lower probability is less steep, the higher is more steep. But in order to break down how we calculate the exponential function, we'll build off that same use case of the Starbucks again. Using the same numbers from the last chapter, the typical customer averaged 18 visits to the Starbucks location over a 30-day period. And this will help just talk about how the Poisson and exponential are kind of like looking at two similar things and can really be used to complement each other. So the Poisson random variable describes the number of visits with the expected value, or the mean of number of visits. And since this follows the Poisson distribution, we can assume that the time between visits follows an exponential distribution. And now we would bring in the numerator of time period to give us a rate of time between visits. So over 30 days, the average time between visits is 1.67 days. And the second formula here shown is the mean value. So knowing this information could then be used for planning how to coordinate staffing and expected stock to order for the week. So rather than how many visits to expect, now we can think the average time between visits. And I mentioned the word rate of time between visits. It's common to define the exponential probability distribution in terms of its rate parameter, which is that Greek letter lambda we just looked at. And this is calculated by taking the inverse of the mean, or 1 divided by the mean, and used to provide as this unit rate, that per day, the rate of patronage at the Starbucks is 0.6, for example, which in application to the real world, we don't have decimal days. So this might be interpreted as, on average, someone might visit Starbucks about every other day. Next, we'll talk about the probability density function for the exponential distribution. So let's talk about this example where a random variable x follows the exponential distribution if its probability density function is lambda e which is that Euler's number that we looked a bit last class, so we take this rate, multiply it by Euler's number, raise that to the negative rate times x. And the mean and the standard deviation of x are equal, and both are 1 over lambda. So the mean and standard deviation are calculated in the same way because of this. And the cumulative distribution function of x is 1 minus e to the negative lambda times x, as you see in the formula here. So the shape of the curve would look something like this. And one example of where we would apply this that would be very valuable to know would be something like the amount of 911 calls during peak hours we would expect to see. This type of decay function that is captured by that negative exponent of lambda. So just showing a distribution of why that makes sense intuitively, that we would start to diminish that over time, where the rate would be higher the lower it is compared to farther out. So we can use something like this to visualize the likelihood of how many 911 calls you might expect to see. So let's go through an example to better explore that formula. And I like that example of predicting time between emergency calls because it's a real business problem for utility companies that need to staff their emergency response team when a gas leak might be reported. They might want to predict how many employees they must staff based on the rate of calls they might expect to happen. So let's assume you're a manager at an emergency response unit and you want to know the probability that a call will be received within a time interval so you can staff the right number of employees for that week. So how would we do this? We would start with something like this, where we would just know that it's an exponentially distributed random variable, and we have a mean of 25 minutes. So you start to measure the time elapsed between emergency calls over an extended period to get this type of mean value, and you find that on average, a call happens about every 25 minutes, which would be very scary, but given like if there was a gas leak every 25 minutes, but let's just use these types of dummy numbers for now. But given this information, let's calculate the rate parameter of lambda. But first, before we dive into different probability rates. Since the mean of the expected value of x equals 1 over lambda, we can compute the lambda as 1 over 25, which is equal to 0.04. Because this is a rate, we can say that each minute we can assume a call will happen 0.04 times. But again, that's not super helpful until we apply it to calculating the probability of a call for a certain time interval. Like on its own, that's not super helpful. So what is the probability that a call does not happen for more than 1 hour? We use the equation to calculate this and place our lambda value in the exponent value and multiply it by x, which is the number of minutes we're calculating for. We use Euler's base, E, and take the output of 0.907. So again, we're just taking our formula, plugging in the right numbers for what it is that we are measuring once we have that rate, and we're looking for that value of x. And this tells us that the probability of a call not happening for more than 1 hour is very small relatively. It's about 9%. So this would indicate that there should be at least 2 staff members at the phone center to accommodate this demand. Here's a curve that looks at what the area under the distribution would look like. We will go through how we would calculate this using Python shortly as well. But before we do that, let's think about the other side of the cumulative probability distribution. What if we wanted to know the probability that you receive a call within 10 minutes? Now we fill in the area to the left of the value that we're exploring and use that same lambda value to calculate the probability of receiving a call within 10 minutes. The only difference here is that we subtract the value from 1 so that we only have the remaining area to the left of the curve when we calculate the probability. By plugging in the numbers in for our calculation in the area to the right of the curve, we have the probability that you get a call after 10 minutes, which is 0.6703. But in this case, you want to subtract that from 1 because we want everything below this 10-minute mark. And the probability would leave us with just about 30% chance. So it's important to make sure that there's somebody on the phone line, staffing this emergency response center, because there's a 30% chance that someone will call within 10 minutes. So this can start to inform the capacity needed from the staffing side. So let's talk about how we would compute this using Python. And then the last section in this chapter will be log normal distributions. Okay. So this will be pretty straightforward of just using the formula and outputting the right answers. So similar to what the homework will look like, you'll have a kind of scenario. It talks about it being exponentially distributed. So that's when you can use these formulas for an exponential distribution, and it'll usually have some type of mean value. So we'll just walk through what we just did for those slides, where we want to calculate the rate and calculate some probability values. So that rate, we have the mean, and using this type of function that I just crafted, which pretty much just takes that and divides it from 1, where it will return that rate parameter. And we can now use that to know the rate parameter is 0.04, which you could just as easily use a calculator outside of Python to do this, or you could also then use Python to say rate mean, 1 divided by right here, and it would return you the same exact thing. So I just use this function, again, to create these building blocks that could be used for other things and just to simplify and, use Python for the power that it can provide. So let's think about what is the probability that a call does not happen for more than 1 hour. And that is equivalent to saying probability of X being over 60. We would define X. And I would use that formula where we take Euler's number and we raise it to the negative rate parameter times X. And that would be that cumulative probability of a value that is above this point. That's why I just wrote greater than. So if you're trying to do anything above a value, you can use this formula exactly. But if we're trying to find the value of something below a value of X, we would subtract that from 1. So on the other side of this answer of what's the probability of a call coming before 1 hour, we could just subtract the same value from 1 and say that it's about 90% probable that you would expect to see a call within an hour, where it's very less likely to not have a call for an hour, or not more than 1 hour. So now we can use the same thing, probability that you receive a call within 10 minutes. We use X, and since this is essentially saying X less than 10, we would need to subtract that from our little function, and we would start to know that there's about a 30% chance that someone will call within 10 minutes. And if you wanted to use a similar stats package that we had for that normal distribution, where you can use something like this to calculate that cumulative density function, feel free. But for now, we can really just depend on those functions, those formulas that I made into functions here for calculating for the homework. All right, Now, to wrap things up, we will talk about one more distribution, which is the log normal distribution. And this is defined with reference to the normal distribution. That's why I wanted to talk about it, because it takes that normal distribution and converts it into log normal scale, because it's just a skewed version of the normal distribution. Where let's talk about what it is that we're actually looking at here, where a random variable y is said to follow a log normal distribution if the log of y follows a normal distribution. So we see this graph that it's positively skewed and relevant for a positive random variable, such as describing income, real estate values, and asset prices. So the key difference between the exponential distribution and the log normal distribution is that the rate is not constant. So you kind of start to see that similar curve that we just looked at for exponential, where you have this rate that then kind of equals out towards the end. But in this case, that we would have more variability rather than that like continuous rate that you would expect to see of calls for an emergency center, where something like the log normal distribution has a little bit more nuance to it. So that key difference of this rate not being constant is when you would start to use a log normal, where that rate might increase or decrease over time. And this has varying applications in the real world, such as modeling the failure time of new equipment. You know, some equipment might not deteriorate at the same rate if there's differences between how equipment's being used, perhaps. Like one is being used very often this month, not so often the next month, use more. You know, we can start to use something like the log normal to capture how the rate might not be constant over time. And the reason why we can use this, because normal distributions may present a few problems that the log normal distribution can solve. Mainly, normal distributions can allow for negative random variables, while log normal distributions include only positive variables. So one of the most common applications where log normal distributions are used in finance is in the analysis of stock prices, where the potential return of a stock can be graphed in a normal distribution. The prices of the stock can be graphed in a log normal distribution. And the probability density function for the log normal distribution is defined by the following equation, where we use different aspects of converting normal to log and vice versa to be able to really get at some of these differences in a distribution. The graphs here show the shape of the log normal density function based on various values of the standard deviation. So as the standard deviation becomes smaller, the log normal distribution starts to actually just resemble the normal distribution. And the mean and the variance of the log normal random variable y are related to the mean and the standard deviation of the corresponding normal random variable x. The summary measures for the log normal distribution can be found here. And we won't go into the equations too much, but it's interesting to just see the similarity to the mean and standard deviation of the normal distribution for a natural log normal value of y can be derived using a very similar version of the formulas. So let's go through some examples for how we would calculate. Let's think of this example where you have penny stocks with an underlying normal distribution. So they have a mean value of $2 and a standard deviation of $1.5. What is the log normal distribution mean and standard deviation for the value of this penny stock? And the reason we're using this log normal is because of that application in real world, because we have this type of compound return that the stock can expect to achieve over a period of time. It's not necessarily this constant rate of growth. It would perhaps compound on itself. We can compute the mean by using our formula and just plug in the values that we're looking to calculate, similar for the standard deviation. And that's all we're doing here. So we can start to think about the positively skewed long tail of the random variable of the price for a penny stock. And because we converted the normal distribution to a log normal distribution using these logarithmic mathematics, we can now use these values as an indicator of the compound return over time, where the log normal distribution is used because it's convenient and helpful model for measurements in exact and engineering sciences, as well as medicine, economics, and other topics. So as long as the underlying random variable has a normal distribution, we can use the log normal conversion to evaluate the natural growth process, which are driven by the accumulation of many small percentage changes which become additive on a log scale. And the popularity of the log normal distribution is also due to the fact that the probabilities of a log normal random variable are easily evaluated because of the normal distribution that we just talked about for the majority of this class. Now we can use the same approach in a log normal situation. So let's go through an example where we use the log normal random variable to find the probability of seeing a value. Let's just think about the same type of penny stock, but now let's think that this stock has a mean, these stocks of penny stocks has a mean value of $5 and a standard deviation of 1.2. We can use the log normal distribution to approximate the probability that the value of Y will be less than or equal to $200. To calculate, we convert the values into a normal distribution in order for us to then be able to use all these different normally distributed tables and probabilities. In this case, we take the natural log of 200 and calculate this, which would be 5.30. And now we can just plug this value into our formula for z-score, and we can calculate that value of 0.25 as our z-score. And because of this, we can just go about our usual way of converting this into a probability using the z-table. And I think it's kind of cool to be able to scale this distribution using the natural log in order to better identify these long tails and be able to work with the normal distribution so that we can actually use the z-score approach. So let's finish off this class with a demo of how we would accomplish these calculations in Python. So we would define our inputs where we take the normal mean. I just indicated that it's normal because we take those normal and we would convert them to being log normal so that we can then use our usual different approaches from the normal distribution. So this formula just takes those equations we reviewed using Euler's number and takes the exponent of 2 times the mean. And essentially it's just taking these values and skewing it to be log normal. So that's kind of what's going on behind the scenes, where this function would take a normal mean and normal standard deviation and convert it to a log format of it. So now this would capture that tailedness of something that we might expect to see. So if we wanted to calculate the probability that Y will be less than or equal to $200, we would define that variable. We would convert that to being log using just numpy.log to convert 200 into a log normal version. And now because of that, we can use our z-score formula, which this is just a function that takes that z-score. And because we are now calculating that using a x that is already converted to being log normal, we don't even need to use these converted log mean and log standard deviations. We use just the normal mean and normal standard deviation. And now we use that x log in here to calculate the z-score. And we can use the stats package to take this cumulative density function for calculating that as well, if we wanted to convert this to just the probability rather than the z-score. So if we wanted to also do that from just the start, we can take the normal mean, normal standard deviation, and calculate this cumulative density function for our log scaled value of x, and we would get that same probability. And so that would be the probability of seeing a value of less than or equal to $200 in the long term, essentially. And using all of those different formulas and functions in Python, you will be able to complete this week's homework, where we talked about different continuous random variables compared to last week, where we talked about discrete random variables. We can now calculate and interpret these probabilities for a random variable under the uniform distribution, the normal distribution, exponential, and log normal. And we can convert z-score back to probability, back to z-score, and really start to use these different metrics to inform the probability of seeing an expected value. And with that, we conclude this week's module lesson.